All right, now that we've seen some nonlinear elements, let's build some circuits containing these nonlinear elements and let's understand how to analyze these circuits. Interestingly enough, I will not really be teaching you any new methods beyond the first three methods that let you analyze nonlinear circuits. I'm just going to use the same methods and, in fact, use the basic node method and then show you how to solve the equations that arise using various techniques. Okay, so really, it's a basic node method that will need to be applied to solve these circuits. So let's start. Let me build a little example circuit for you using the hypothetical expo-dweeb that we defined in the previous lecture. So let's start with a little circuit. So let's say my circuit contains a voltage source with a voltage V and has some resistance R here, and then I connect my little hypothetical device, the export dweeb out here, and VD and ID are the currents. ID is the current that flows through it, and VD is the voltage across the device. Okay, so this device here is none other than my hypothetical export dweeb. So let's take a look at how we might analyze a circuit like this. Okay, a circuit containing some linear elements, and there is this non-linear element, and it's non-linear because, as you can see, ID relates to VD. Okay, so before we begin, I want to show you a little trick. One of the things that you will see a lot in 6002X and in circuits courses and in engineering practices in general is that engineers like to deal with patterns. Once we figure out a way of doing something, then even though we may have a lot of choices, we continue to keep reusing that pattern. And in circuits and electronics, I'm going to identify whenever we come across a pattern, I'm going to identify that pattern for you so that you can remember that and cast that in your mind as something to bear in mind as you build future circuits. So these patterns are really, really critical. So notice here that I showed you a pattern. Okay, I had a voltage V here, a resistance R, and there is a pattern in the circuit. This pattern is some funky little device that is here. In this case, it's a nonlinear device, but in general, it could be any strange device. Okay, whether it's nonlinear, whether it's some other interesting device, but let's say we identify that as any funky element. Okay, but if you look to the left of that device here, I have my usual stuff. I have a voltage source in series with a resistor. So I claim this is a very important pattern. Okay, where the pattern is a voltage source in series with a resistor, and then the series voltage source and resistor are connected to some interesting device in a series connection. Okay, so I claim this is a very important circuit pattern. Okay, so what do you think? Why do you think this is a very important circuit pattern? So consider the following situation. Okay, so consider that I have my device here. Okay, no surprises there. And let me mark out the VD and ID for this device. Okay, that's the same funky little device. And so at the terminal pair, let's say my branch variables, let's say I identify a V and an I, where I is like this. Okay, let's just for kicks identify a V and an I at that little pair of terminals that I defined here. So now let's do something very interesting. So let us say that I have some big circuit connected to that interesting little device. Okay, and that big circuit, some circuit network N, contains a whole bunch of elements. It could have a bunch of linear resistors. It could have a bunch of linear voltage sources, and it could also have a whole bunch of linear current sources. Okay, more resistors in some arbitrary connection. This is an arbitrary linear circuit. So this circuit here on the left-hand side is an arbitrary linear circuit. They could have all kinds of connections of linear elements. So now do you see where I'm going with this? Okay, do you notice the key trick here? So the key here is that if I have this arbitrary circuit here, but if it's composed of linear elements, and then what I've done is I've taken this funny little device and yanked it out of the rest of the circuit and pulled it outside. Okay, so it's as if I have a bag of stuff, and let's say there's something interesting, What I've done is I've pulled that interesting thing out of the bag, but leaving the rest of the bag as a linear stuff, but the interesting thing has been pulled out. Okay, but everything else is linear inside that bag. So now what the trick here is that I can take this entire bag of linear stuff and recall the famous Thevenin method. Okay, I can replace this huge bag of linear stuff with the Thevenin equivalent given by the V and R, the voltage source in series with the resistance. Okay, so this huge network here, okay, for the purpose of analyzing I and V, can be replaced by a Thevenin equivalent that I show here. Okay, so you see the magic of this? If all I cared about was just the voltage and current here, then I can take the entire network, okay, the entire linear network, completely arbitrary, and I can replace that with its Thevenin equivalent shown here for the purposes of computing V and I. Okay, so suddenly I can take this arbitrary circuit and replace that with a Thevenin equivalent and then simply have the device, the strange device on the outside. Notice that this strange device, which may be nonlinear, cannot be contained inside the network because since it's nonlinear, I cannot replace it with a Thevenin equivalent. So I really have to pull it out. And if what I'm left with is a linear network, then I can replace it with a Thevenin equivalent. Now this is extraordinarily powerful. Why is it extraordinarily powerful? Okay, the reason is that if I show you, okay, how to analyze this circuit pattern, okay, that is a simple circuit pattern containing a voltage resistor connected in series with a funky little device. If I can understand how to analyze the above simple circuit pattern, then what it means is that I can analyze any one of the more complex circuit patterns at all. Okay, so once I understand how to analyze the V and R in series with the funky little device, then what that means is that I can now understand how to analyze any other circuit that is linear connected to this funky little device. Okay, this is truly extraordinary. So which means that we really don't have to go through 50 different circuits. We can just analyze this circuit one, and once we understand it, we are done. Then we can always replace the rest of the circuit with a Thevenin equivalent and then go ahead and analyze our device in the context of the rest of the circuit. Okay, this is just extraordinarily powerful.